In this video, I will try to derive the I think its name is called Considere criterion, which is also known as the necking criterion. It is the criterion to tell when the necking is happening in the sample, which is the d sigma t over d epsilon t larger than or equals to sigma t. So I will derive this criterion step by step. But first of all, in a typical stress strain curve, we should plot first. For engineering stress and engineering strain, the engineering stress strain curve usually has a ultimate point. This is the largest point of the curve. We denote it as the UTS, ultimate tensile stress, which is a very important parameter of the material to tell the physical property. And the true stress strain, we can also plot another curve with true stress and true strain. But in this curve, it's kind of difficult to find the UTS point, because the UTS point is just the necking point. Because when necking happens, the stress just falls down, because this is the end of the strain hardening. End of strain hardening. Because before this point, when external force become larger, the strain becomes larger. It's like as the strain increase, the strength of the material increase as well, which is known as strain hardening. Like in this area, say the external force is always increasing as the strain increases. So first, let's recall these expressions of stress and strain. Engineering stress, engineering strain, true stress, true strain is equals to sigma 1 plus epsilon is ln 1 plus epsilon. Engineering stress is the external force divided by the original cross-section area, A0, which is a constant. Right, so in this expression, this equals to A0 times sigma. So we can put this constant out, and equals to A0 d sigma d epsilon. This larger than equals to 0, and because A0 is a positive value, because this is the cross-section area, you cannot get the negative one. So just wipe it out, and resulting in this expression, which means the slope of the curve is 0 when the necking happens. So if the slope of the curve is positive, this area is the strain hardening area. This is quite straightforward, but in the true stress strain curve, what I want to prove in this video is that these two expressions are basically the same. So you can tell the strain hardening area based on true stress and true strain, because when we are trying to modeling the material, we intend to use true stress and true strain, which is more true. This is like it is more accurate. So we want to know how to derive this strain hardening area and necking point in the true stress, true strain curve. So in the previous video, we know that necking is like this. End of the so at this necking point, the strain hardening ends, and when you add more external force, it will break into two pieces. So necking is very important, and we want to know when the material will necking happens. This is a very important parameter. So first of all, let's derive these expressions first for further improvement. This equals to E over epsilon t minus 1. Yes, and then sigma equals to sigma t over divided by E over epsilon t. Yes. So for this expression, we know that d sigma over d epsilon t times d epsilon t d epsilon larger than equals to 0. And for the right side of this expression, this is very straightforward. It's just d epsilon ln 1 plus epsilon. This is just 1 plus epsilon over 1. This is very straightforward. But for the left side of this, cos sigma equals to sigma t over sigma t times E over minus epsilon t. This equals to, the left side is equals to this, but you can't just get this sigma t out, because this is not a constant. It is related to epsilon. So you need to use another that like du v equals to u dv plus v du. You need to apply this equation into solving this. So it's like this equals to sigma t d epsilon t E minus epsilon t plus E minus epsilon t d sigma t d epsilon t. Right. And for this one, we can further derive this equals to minus E over minus sigma t. Yes. So after all, this comes with minus sigma t over 1 plus epsilon times E minus sigma t plus E minus epsilon t times d sigma t d epsilon t larger than or equals to 0. And since this one, they are all positive, and 1 plus epsilon is also positive, obviously, so we can cancel it as well. So after all, we get this d sigma t over d epsilon t larger than or equals to sigma t, which is the Napkin criterion.